Let us see about PN junction diode and the current equation of PN junction. While we are seeing this semiconductor, the semiconductor, it is a material which has the electricity conductivity to a degree between that of a metal and that of the insulators. And while we are seeing this, some of the semiconductors are the foundations of the modern electronics, including transistor, solar cells, light emitting diodes, quantum dots, and digital and analog integrated circuits. And there are two types of semiconductors, that is intrinsic semiconductors and extrinsic semiconductors. While we are seeing the intrinsic semiconductor, it is the pure impurities that can be doped into that particular semiconductor. That is, it consists of equal number of electrons and holes in this intrinsic semiconductor. And while we are taking this extrinsic semiconductor, that is, impurities are added to the extrinsic semiconductor. And also here the dope, that is, while we are doping, the doping agent has been introduced, and there are different electrical properties than that of the extrinsic semiconductor. And the extrinsic semiconductor, they are again divided into N-type semiconductor and P-type semiconductor. In the case of N-type semiconductor, extrinsic semiconductor with a larger electron concentration than hole concentration are called N-type semiconductor. And the case of P-type semiconductor, that is, the hole concentration is more when we are comparing to this intrinsic semiconductor. Here PN junction diode. Well, we are seeing this PN junction diode. This is the diagram for this PN junction diode. That is, when a P-type and N-type semiconductor materials are first joined together, a very large density gradient, that is, exists between the sides of this junction to form free electrons from the donor impurities there to migrate across this newly formed junction to fill up the holes in the P-type semiconductor, that producing the negative electrons. And also, the total energy on each side of this junction must be equal and opposite to maintain a neutral charges conduction around this junction. And here, in this case of depletion region, that is the region formed in between the P and N-type is said to be the depletion region. In the case of depletion layer region has a distance d, and here there may be a silicon distance of d drop of the positive sides, and that of the distance of dn of the negative side. And here it gives the relationship between the two, that is dn into an equal to dn into nd, in order to maintain the charge neutrally, and it is said to be the electrons. That is, we can see it is concentration. And here, while we are seeing the function, that is depletion layer, here this is the depletion layer of N-type. Here, the one side of the crystal, that is the pure semiconductor, germanium, is doped with the acceptor impurity atom, and the other side is doped with the donor impurity atom, and the PN junction is formed. It is shown in the figure, and the P region has high concentration of holes, and N region contains large number of electrons. And also, when we are seeing this, the junction is formed, and the free electrons and the holes crosses this through the junction by the process called diffusion. And during this process, the electrons crossing the junction from N-type to the P-type and recombining to the N holes in the P junction region very close to the region. Similarly, the holes also crossing the junction from the P region to the N region recombine the electrons in the N region very close to the junction, and this forms a region, very close to the junction, and this is formed which does not have any mobility charge very close to the junction, and this region is said to be the depletion region of the PN junction diode. And here let us see the function. That is, while we are seeing the function, an electric field is set up between the donor and acceptor ions in the depletion layer of the PN junction, and also the electrons in the N side are penetrated to go into the lower potential of the P side. Similarly, the holes in the P side then forms themselves at a lower potential and prevented to cross to the N side. Thus, there is a barrier at the junction which opposes the movement of the majority charge carriers, and the difference of potential from one side of the barrier to the other side of the barrier is known as the potential barrier, and the potential barrier is approximately 0.7 volt for the silicon PN junction, and it is for 0.3 volt for the germanium PN junction. And also, the distance from one side of the barrier to the other side of the barrier is said to be the width of the barrier, which depends upon the nature of the material. That's about the PN junction diode. Now we can see the current equation. Here, to deliver the expression for the total current as function of applied voltage, we can say, let us connect this in the forward bias junction. Therefore, the equilibrium current I equal to I naught into e power v by divided by eta vt minus 1, where I is the diode current and I naught is the diode reverse saturation current at room temperature, and V is the external voltage applied to the diode, and N is a constant, and it 1 for germanium and 2 for silicon, and Vt equal to Kt by Q, and here K is the Boltzmann constant and Q is the charge of electrons and T is the temperature of the diode junction. At room temperature, the current can be given by this equation, that is I equal to I naught into e power 40 V by eta minus 1. For germanium, it may be vary, and for silicon also it may be vary depending upon the material that is doped into that particular PN junction diode. And here, if the applied voltage is greater than unity, then the equation of the diode, that is equation of the diode current for germanium is given by this equation, that is I equal to I naught into e power 40 volt. Here for silicon it is again varying depending upon the material, and here and diode current can under the reverse bias can be given of I equal to I naught into e power v minus v by eta vt minus 1, and here if v is very much greater than vt, then the term is less than 1, therefore I equal to I naught. This is said to be the reverse saturation current, which is valued as long as the external voltage is below the breakdown voltage. Thank you.